G'day everyone, welcome to the second video of the Introduction to Quantum Field Theory, and today we're going to talk about the Casimir effect. So we'll investigate one effect of the vacuum, and usually this is done using the photon field as it was done in the original paper by Casimir, but we will actually use what we already know, which is spin zero particles. We're going to make lots and lots of simplifications to this, starting by using a neutral Klein-Gordon field so that the field is Hermitian. And that means that particles are their own antiparticles. At first, that's going to cost us a little bit because we'll have to write a new Lagrangian and a new Hamiltonian, but then it'll make things easier after that. And also, this assumption makes it closer to the photon case because photons are also their own antiparticles. We'll introduce the other simplifications as we go. The first one will be that we'll have we'll make it massless, and we'll also make it a one-dimensional field. So let's get started. So we're going to need to write down a field operator for this case. And because the particles are their own antiparticles, we can write the field operator as a sum over all the momenta. And Px here is P mu x mu. And so now, because the particles are their own antiparticles, AP will destroy a antiparticle, and AP cross will create a particle or an antiparticle. Last time we couldn't write the creation operator and the destruction operator in the same phi because we had to conserve charge, or we had to conserve, quantum numbers generally. Now that each particle is its own antiparticle, there are no quantum numbers to distinguish between the two. So we can actually write AP and AP cross in the same field. The Lagrangian now is a little bit different. It has an extra factor of a half, which you may like to verify by making the Euler-Lagrange equations and showing that you get the correct Klein-Gordon equation. And similarly, we will get the Hamiltonian, which is a factor of 2 smaller than what we had before. So we'll have so that's what it's going to look like, and then we're going to enforce our commutation relationships. And we'll get this factor of a half is our vacuum expectation value, which still goes to infinity. Okay, now imagine I've got two very large parallel plates separated by a distance a. And in the original paper, the idea was that you've got some very large conducting plates, and that forces the photon field between the plates to go to zero. Sorry, not to go to zero. Not the field between the plates, but it forces the photons to have boundary conditions such that the field is zero at the plate boundaries. And so this spacing here is A, and we would write, in fact, for this case, we're just going to do it in 1D for simplicity. And in 1D, we're just going to have that the wave function at the left plate and the wave function at the right plate vanish. So that's kind of the setup, and we're going to do it in 1D, so we won't have the so it'll make it slightly easy for us. So with these boundary conditions, I can write the wave function in 1D, so just x and t, or z and t or whatever, sum over n. And what I'm going to do here is I'm separating out the spatial part from the time part. And I'm actually adding the positive momenta and negative momenta contributions together because I want to get standing waves between the two plates. So because it's standing waves, I can write this as sine kn x, where kn is equal to n pi over a, and n is a positive integer. So this quantizes the momenta between the two plates. So now we have just for the space between it, the momenta is quantized. We can't have any value of momentum we like. We can only have certain values of momentum, and we have to have the same going to the left and going to the right, so that we end up with a standing wave with the correct boundary conditions at 0 and a. So the vacuum excitation value between the plates is a half sum over n omega n. So just looking back at our equation here, that's that factor of a half, and it was a half times EP. Now it's a half times omega n, where I would say that omega n squared equals kn squared plus m squared. And the reason why I'm using frequency rather than energy is because I'm about to lose the mass as well. And then it looks a little bit more natural to have frequency rather than energy, but it really doesn't make a difference. By the way, just pointing out, this is infinite. It's still infinite. It's discrete, but it's still infinite. It's still positive infinity. Okay. On the other hand, without the plates, I don't have to worry about those boundary conditions. So I still want to work out how to calculate the energy. And the standard transformation is you take 1 over v times the sum over n, and you want to make it continuous. It becomes 1 over 2 pi cubed integral over the volume d cubed n. So that's the standard way of making the transformation from the discrete to the continuous. So in our case, because it's a 1D transformation, we'll have that the energy per unit length is equal to 1 over 2 pi integral from 0 to infinity dk omega k, and omega k is just square root of k squared plus m squared. And again, this is infinite. In fact, I shouldn't say between the plates. I just say the contribution within the region 0 to A, because the plates aren't there in this case. We're in the without the plates case. So this part is E0 vacuum with no plates. That's A over L times E0, or A times the energy density. So it's A over 2 pi times the integral 0 to infinity dk omega k. of course, that's still infinity. Lots of infinities. So the point is that both the energy between the plates when the plates are there and E naught vacuum between where the plates would be if they were there are infinite. Because there's infinite energy density in either case. But they're not equally infinite. Not all infinities are the same. And so what we're going to do is regularize these infinities, and then we can renormalize. So one more approximation. Take the mass equal to 0 so that omega n equals kn equals n pi over a. So let's do the easy one first. No, let's not do that. Let's do the hard one first. Neither of them is too hard after we've made all these approximations. So what I need to do is I need to write the energy in some way which I can get rid of the large infinity and just have something left over. And so this is called regularization. And if I write something like this, that's omega n e to the minus pi n over a times delta. And you can see in this equation that as delta goes towards 0, then that exponential term will go to 1, and I'll be left with a half times the sum of omega, which is exactly what I expect to have. But now I've introduced this kind of delta parameter, which is going to go to 0 and will restore the full equation. But in the meantime, I can now actually work with it a little bit more easily. And I'm not going to go through the full mechanism of the details here, but essentially what I can do is I would take this and I'll go, okay, it's a half. If I do this, minus d delta, it's a derivative with respect to this delta. And so then I'm going to integrate this term on the right. And if I integrate that with respect to delta, I just get e to the minus pi delta over a times n. And I've switched the delta and the n in the exponent just to clarify things a little bit. And so you can see that if I take the derivative with respect to delta of each term, then I get back to what I'm supposed to get. And so then I can treat this guy here, this sum, is a geometric series. Yeah, and then so I can work out what the limit of that geometric series is. And then I take the derivative back with respect to delta, and I will end up with, pi over 8a sine h to the minus 2 to a. Of course, you could leave it in terms of exponentials, which I would prefer to do, or you can get Mathematica to do it, which I would also prefer to do. But a nice way of writing it is sine to the minus 2, so 1 over sine squared of delta pi over 2a. And of course, the n has disappeared because that's just the index of our geometric series, so it goes away. And now I've got this limit of a sine to the minus 2 of pi delta over 2a. So this is a small parameter. And so then I can write this as an expansion over delta. So expand over this small parameter. In fact, it's not so difficult. You plug it into Mathematica and you ask Mathematica to do it. The answer is 1 over, so shine to the minus 2 of x is 1 over x squared. So that's going to be 4a squared over pi squared delta squared. Then you get minus a third, which does not depend on the x, plus something of order x squared, so delta squared. So that's plus delta to the 4, blah, blah, blah. But the point is that that is the leading terms as delta tends towards 0. And so you can see that the first term there is indeed infinite. It's a over 2 pi times delta squared. And the second term doesn't depend on delta at all. It's just pi over 24a. And then all the higher terms have disappeared because they're of order delta squared, delta to the 4, and so on. And now delta has gone to 0, so they've gone. So now we've actually regularized this. We have the first term containing all of the infinity. It's 1 over this delta squared as delta tends towards 0, so that's very infinite. And the second term is finite. That's regularization. So now we can work out the case without the plates. Without the plates, we have, for the vacuum, it's a over 2 pi. Again, we have to regularize this somehow. And we'll do the same trick. Delta tends towards 0, integral from 0 to infinity dk of k e to the minus k delta. And so you can see that as delta goes towards 0, the exponent will go to 1 again, and we'll just be left with dkk, which is, k is equal to omega, remember? So this is what we want, because it's massless. And so then if I write this as a over 2 pi, I've got a limit as delta tends towards 0. I'll take the negative derivative of delta, same way as before, integral 0 to infinity dk e to the minus k delta. And because you can swap the derivative dd delta with the integral in calculus, and so then probably some mathematician would have my head for that, but I'm all right with it. So that's a over 2 pi times the limit of delta tends towards 0 minus dd delta. Now I can actually integrate this thing. I get e to the minus k delta over minus delta. It's a integral like this, and that's equal to and now I need to take the derivative, one more step, d delta of this thing. It's minus 1 over minus delta, so that's the derivative of, it's time to get rid of this guy. It's the derivative of 1 over delta, and that means it's the limit as delta tends towards 0 of a over 2 pi delta squared, because the derivative of 1 on delta is 1 on delta squared with the minus sign, which gets cancelled out by the other minus sign. So the good news is that this looks exactly like the first term from our from the case that has the plates. So if I look at these two infinities, I can see that the difference between them is actually finite. The difference between the two infinities, delta E naught, so it's the change in the infinity, is E naught for the plates minus E naught for the vacuum without the plates, is now just equal to minus pi over 24a, which is finite. So that's the process called renormalization. You regularize and then you renormalize. So this is the energy that's stored between, this is the change in the energy when you put the two parallel plates there. And so what does that look like? It means that you've got some delta E naught versus A, and it's 1 over A like this. So if I'm at if you have the plates at some point, you can see that there's some force in that direction, making the plates go closer together. And you'd write that the force F A equals minus the derivative with respect to A of delta E naught, which equals minus pi over 24a squared. So it's attractive, which is easy to understand. So basically you've created a negative energy density between the plates, and the closer the plates get together, the lower their energy difference is, and so it's an attractive force bringing these two plates together. And it comes from this vacuum expectation value. And in fact, you can put the mass back in. It's pretty easy, but then the force itself becomes mass dependent. And it's just a little bit messier. So then there's like a low mass limit and a high mass limit. If we go back to photons, which are massless, and we're in 3 dimensions plus time, then we'll get that the force per unit area of the plates is equal to minus 1. I'm not going to do the calculation, obviously, I'm just showing what the answer is. You get minus 1 over a to the 4, and that's a to the 4 is because you've got a three-dimensional case, so you get this force over a has to have these units. Pi squared over 240 turns out to be the factor between two parallel plates of area A separated by distance little a. And in fact, an experiment similar to what I've just described was done in Los Alamos. If I remember correctly, it was a metal sphere and a surface like this, and it was to calculate the force between separated by some distance. So then you separate these guys by some little distance here. It was just floating off, and so that one, so it's just a metal ball and a metal plate, and that was done by Stephen Lamoureux when he was at Los Alamos in '97, and I'll post that on Moodle. Slightly different geometry just to make it easier to do the experiment, or possible to do the experiment. But that was the kind of first experimental confirmation of the Casimir effect. And so we see that this plus 1/2 h bar omega is not completely made up. There's something serious going on here. We have to take it into account if we want to understand phenomena that we can measure. So that's the first part of quantum field theory. The plus infinity actually exists.